All right, so let's just do one example of a problem involving Bernoulli's equation. This is a very standard problem, and it's fully worked out on the slide, but I think it's a good idea to look at this problem together. So, so what is this problem saying? It's saying that you have a cylindrical water tank that has a small hole in its side below water level. You are given the y, the height of the hole, and you're given the height of the water. I mean the depth of the water. That's y2. Okay, and you have to find out the velocity of the water as it's flowing out of the hole. Okay, so how do we do this? Well, when you apply Bernoulli's equation, the strategy is always to choose two convenient points and use the fact that p plus half rho v square plus rho gy would be the same when it's evaluated at those 2 points. That's always the strategy. Now you can choose any 2 points you want, but it's convenient to choose points for which we know something. So one fact that we've often mentioned throughout this chapter is that if a certain point is in contact with the atmosphere, what is its pressure? It's going to be atmospheric pressure, right? So it's convenient to choose one point over here and another point right here. So our point 1, let's say, our point 2 is on the surface of the liquid, and our point 1 is somewhere at this hole where the liquid is gushing out, right? So both of these points are in contact with the atmosphere, so we know what their pressures are. They're just atmospheric pressure, right? Let's apply Bernoulli's equation to both these points. So P1 plus half rho V1 square, and that V1 is what we're looking for, plus rho G Y1 is equal to P2 plus half rho V2 square plus rho G Y2. Okay. So the P's are P1 and P2 are both equal to P atmospheric, I mean. So I can just cancel these two out. And so I'm left with this simple equation, 1/2 rho V1 square plus rho G Y1 is equal to 1/2 rho V2 square plus rho G Y2. Now I would be able to solve for V from this equation, but there is one problem. I don't know what V2 is, right? I do know what y1 and y2 are, so I'm almost there. I just need to figure out what v2 is. So I told you that in Bernoulli's equation problems, sometimes you also have to use the equation of continuity. So what does the equation of continuity give us? Let's say that this area is A2 and this area here is A1. The equation of continuity gives us A1 V1 is equal to A2 V2, and V2 is the velocity with which a particle of fluid is moving on the surface. Obviously that's going to be in the downward direction because the level of water is gradually going down, but it's at a very slow pace. So you can see that V2 is going to be much smaller than V1. Just from the equation of continuity that we just wrote down, you can see that V2 is going to be A2 divided by A1. Sorry, A1 divided by A2 V1. So that implies that V2, since A1, the problem tells us that A1, the area of the hole, is much smaller than A2. You can see that V2 is much smaller than V1. So that means you can just ignore V2. In this problem, it's okay to just ignore V2 in comparison to V1. So you could just ignore this term. It's approximately 0. So from there, you can solve for V1. So v1 square is equal to, if you just rearrange things a little bit, 2g y2 minus y1, and so if you take a square root, you get v is equal to, v1 is equal to 2g y2 minus y1, and that is the answer. Okay, so that's pretty much how you do Bernoulli's equation problems, and that's all there is to this chapter. So I'll just end the video here.